Well, hello everyone. In this section, we're going to talk about Retrieval Augmented Generation. So in GenAI, Generative Artificial Intelligence, there's this concept of being able to take a corpus of data using a large language model to be able to have a conversation with that data. And that's often called Retrieval Augmented Generation, or RAG for short. So let's dive into it, into the code. So first of all, let me shut this down and move over to a notebook we'll be using today on Retrieval Augmented Generation. But before we get started on actually writing the code that's going to do that, I need to stop and explain a few things. How we're going to be able to do this goes by way of understanding a little bit about sentence transformers themselves. First of all, what is a sentence transformer? Well, it turns out that you can build a model that will take a phrase or a sentence and push it into high dimensional vector space to represent it. And each one of those vectors, each one of those dimensions is a different aspect of that sentence. Now, we don't intuitively know what all those are, but we can kind of guess. Some of it could be related to, is this thing inside, outside? Is it hard or code? What sort of degree of color is it? What sort of similarity does it have with other things? I think a good way of looking at it would be take just a single word, like the word apple. When you say the word apple, are you referring to the fruit? Are you referring to a computer? Or are you referring to a record company? Well, in the context of a sentence, you would understand that. And that's what these sentence transformers do. They're able to understand and then connect meaning to phrases, to words, and even larger corpuses of data in a high dimensional vector space so that inside that space, things that are similar are close together. Well, let's do this. Let's start, first of all, by embedding some of these sentences into that space. I just want to show you what it looks like. So in this code, we'll let it run here. We are loading up this sentence transformer model, and we are going to push these three sentences into that, through that model, into that vector space, and then print out what that embedding actually looked like. The embedding being sort of if you think of the XYZ coordinates, but in this particular case, like over 700 different dimensions of those specific embeddings or coordinates inside that high dimensional vector space. So here's the first sentence. This is example sentence. We see that one right here. Here are the embeddings, right? So if you take a look at this, all these different dimensions and then this floating point value, so representing it where it sits in that vector space. And every one of the sentences are represented here. All right, well, what does that mean for us? What does that do for us? Well, it turns out that if we do this, we can use math, geometry, to start to determine how close something is in similarity to something else. And that's what we find from these for these sentence transformers that's super helpful. There are vector databases, that is, ways of storing this. We could obviously just do it in memory like we did up here, but we could also store it into a vector database that has a lot of acceleration and optimization to be able to process all these different vector points, all these different documents or sentences within this space. And I think we were just talking about like apple is a fruit, apple is a company. Here's an example of like to some degree squished down to 3 dimensions, but instead of the 700 plus dimensions that would exist, but gives you an idea of like what that could be. Apple and similarity. There is some similarity in the word, but is the computer company is completely different than the fruit, and that fruit's a lot closer to a banana. All those different things would be placed into these vectors, into this vector space, and could be stored in specifically a vector database. Now, a lot of them vector databases. We're going to be, in our example, we're going to use Chroma, but there are many others. Weaviate's another one I've used. And pretty much all of your traditional vector or your regular databases are now adding vector components to it. So Postgres has a vector addition, and we're going to see probably that proliferation continue, right, as more and more need for this type of thing happens. Now, why is this important? Let's kind of get into the value out of this, right? I mentioned that we can have all of these different documents stored in this high dimensional vector space. And using these geometric tricks, we can detect which of these vectors are closest to each other into this space. And using that, we can actually start into a semantic similarity between those two different connections. And let's actually test this out. Now, this is not using a vector database. This is just purely using the math and the science behind these sentence transformers are able to do this translation. We can do some computation to figure out which are closest to these two documents, right? So here are the documents that we're going to use. These are sentences, but think of them as documents. We have the quick brown fox jumps over the lazy dog. If you saw my last video, you know I get hung up on that, but I think it's a good it's a good sentence. Covers all the letters in the alphabet. But the second, look, a fast brown animal leaps over a sleeping canine, and then we have artificial intelligence and machine learning are transforming the world. And then we have self-driving cars are using machine learning for navigation. Okay, so let's take those 4 documents and we will embed them into this vector space using that model. Well, this is the model again, and we're going to use that model to encode them into that space. And so we'll get back what we saw earlier, these big arrays that are representative of those dimensions inside that vector space. Now, let me pause there and just, how did it actually do this? Turns out this model was trained on a massive corpus of data, and in using transformer technology that we have covered in the previous session, it's able to make those connections and create models and associations, embeddings that will intuit between 2 different sort of concepts. And it's able to bridge those together. And so this model was trained on large amounts of data to be able to do just what we're seeking it to do, which is give us something that's associated with this document. What's the closest thing to it? And that's really what we have here. So here would be what we're going to do here is we're going to send a query. What technologies are used in autonomous vehicles, which would be like this query dot here. What we want is, based on this corpus of documents that are also in this vector, tell us what's closest to it. Right? What is that cosine similar document in that space? Okay, now if we look at this, what should we see? What do you think should be the answer to this? Now, if we look at each one of these, it's probably not the first 2, right? This one's about artificial intelligence, right? And autonomous, but it says specifically autonomous vehicles. Well, the only thing about autonomous vehicles is this one right here. Well, let's see what happens. In fact, you'll notice there's actually no similar words. It's used in cars here, machine learning, and it doesn't even say autonomous. But can it detect the similarity here? So what happens in the code, we're going to take that query, similar to these documents, we're going to embed it, encode it, into using this model into that high dimensional vector space, and then we're going to get some scores. The scores are, what's the distance between this query and this document? This query, this document. This query, this document. Do you get the idea? And so it's going to tell us, it's going to give us a result set of using cosine similarity, what are the closest documents, and give us that order. And what we want it to give is the most similar document, right? What's the one that is closest together, the closest distance. So there's our code. Let's run it. Let's see what we get out of this thing. Ah, we got the right one. self-driving cars are using machine learning for navigation is the one that's closest to what technologies are used in autonomous vehicles, right? So it makes sense, right? Makes sense. But isn't that powerful, right? So you can see how this would be useful. Notice it's not because it's matching words, word to word, it's literally matching concepts. And that's the power behind this. How does that help us with Retrieval Augmented Generation? Well, it turns out what we're looking for is something similar to this. I want to be able to ask a question of my very smart large language model chatbot, think ChatGPT. I want to be able to ask it a question. And what I want it to give me would be an answer that is using documents that I load into the vector database. Now, why would I want to do that? Well, it turns out that most of our large language models that we have access to, ChatGPT, etc., don't have access to, and thankfully so, right? Don't have access to my personal documents, unless I put them out on the internet that happen to scan and use for training. And so they won't know things that it hasn't trained on. In fact, there's a point in time in the past where that training ends. Well, if I need to know something relevant today, and maybe I have a document that I just wrote today or last week, I want an answer that may be pulling from that document. In fact, I could have a whole corpus of data, documents that my company uses or I use personally for research that I would want to have available for my chatbot to be able to reference to provide an answer that's relevant and grounded in it. Which gets to the second point, which is one of the things we do see out of a lot of these large language models is that if you ask it a question, it's going to answer you, whether it knows the answer or not, right? And it won't say it doesn't know the answer, right? It's actually going to give you an answer. It's going to make up one. And that's called hallucination. It's going to sort of dream a story for you. And that's what we can see from these large language models. Well, what we want is to ground it into some facts, into some documents that we want it to use to provide the exact answers back to us. So we're actually going to build one of these. So hang on to your seats. Here we go. Let's build the code that will actually do exactly this. Here's what I propose. I have a blog that I have written for the last several years, articles on a weekly or monthly basis about all sorts of topics. And I want to use that as my vector database, my repository that I want to feed into the vector database. And so the first thing we want to do is let's encode those blog posts into our vector database. So we'll start here. I do need to run and import. Oh, pay no attention to the error. We do get errors every so often, but this was giving me some advice, something I need to be doing differently. But it did work, and it looks like we did load everything we need to load. Now let's go down here. So let's start. We're going to actually use Chroma, as I mentioned. I'm going to start that, and Chroma started. So this is a vector database that just runs in memory and will store its data in this folder here called data. So it's a lightweight vector database. You can easily instantiate, initiate, and store documents in. So we're going to do just that. We'll call it my name, which is actually the website that it's going to be pulling from. We're going to initialize we're going to have documents, we're going to have some metadatas, and we're going to have some IDs that we're going to load in. And I'm going to pull it down, all of the documents from this JSON feed as part of the blog. So let's do that right now. It's pulling the blog feed. It's pulled in 197 different blog posts, documents. Now we need to index those. So what we're going to do here is we're going to take each one of those, break it apart with title, the URL, like the reference point, where it is, because I may want that later. I may want to actually provide the reference after I do the generation of the response. And then I'm going to take the body of all the text and convert it into regular text. So anything that would be formatting data, we'll remove, and we'll just store that document into memory. There we go. We loaded all the documents into memory. All right, now let's encode them. So we're going to use that model, like we talked about earlier, to take each one of these documents and push them into that vector space and store it into the Chroma vector database. So I'll run that now. It'll take a bit. There we go. The collection has been generated. So all 197 documents are out there. They're now stored in the Chroma database. Now here's what I want to do. I want to ask it a question. Remember this this example up here, right? We had it ask a question and we got a result. Well, I want this query the vector space. We want to send this query over and we want to get back a result set. So the query I'm going to ask is give me some facts about solar in California. So that's the query we're going to ask. Let's go ahead and run that. Oh, so, and by the way, I did ask it to limit it to 5, and it says, yep, you got 5. There are 5 documents. Well, let's see what those documents are. Let's unpack those. There they are. So here's what the vector database gave us for my query. Give me some facts about solar in California. The first thing it gave was California solar net metering. Turns out I wrote an article on that, right? And the next one is 23.5 degrees, which is actually the tilt of the Earth, which is very important in the solar cycle as the Earth goes around the sun and how that affects our seasons, right? So a whole article is written on that. And all of these actually have something to do with light or solar, very connected. And no surprise, because we've seen how well these the semantic similarity between these things getting handed back out of these queries can be from a relevant standpoint. Okay, now I'm going to reset our database, but we have our documents. Now, remember back at this this diagram, the one thing I want to do is once I get that result set, I want to feed that into the large language model because I want it to summarize and give me back just the answer I'm looking for, some facts about solar. But what we actually got back, if we were to take a look at, let's do that. Let's actually take a look at what we have coming back here. What is this context string? Let's run this. This is what we actually got back, which is all of these documents in their full text. And it's a lot, right? You can see a lot of things here, right, related to solar, no surprise, right? Right, all of these documents are here, and there are a lot, right? So we'll clear this. What we want is our large language model to actually distill down and give us a summary. So this is how Retrieval Augmented Generation works. We have retrieved, that's the first R, right? Retrieval Augmented Generation. We have retrieved back context data that we want to inform the large language model to use. We want it now to augment its answer and generate a response to us based on it. There you go. Now it's RAG, right? Retrieval Augmented Generation. You got it. So here you go. So the way that we do this is we create a prompt. And the RAG prompt is this. You are an assistant for question and answer task. Use the following pieces of retrieved context or augmentation to answer the question. If you don't know the answer, just say that you don't know. Back up your answer using facts from the following context. Okay, and then we're going to say, here's the context. And we're going to plop what I just showed you right in here. And we're going to plop the question we want it to answer, which is this right here inside of this RAG prompt. So I'll run this. And if I were to print that, that's going to essentially be everything we just took a look at. In fact, I'll just do it here, and you can see the raw code of it. We'll just run that, right? That's what it looks like. Here's the body of it. You are an assistant for that whole thing that we saw there, plus all this context, right, that it now has that it can do something with, right? All right. Well, so what do we do with that? Well, here's what we do with that. We want to connect to our large language model, and what we want to feed into the model, this prompt. You are an assistant, right? Use the following, this is the instructions for it. Use the following pieces of retrieved context to answer the question. How do we do that? Well, I'm going to use the OpenAI API, and I'm going to use the a Llama 3.1 8 billion parameter model that I happen to be running on my hardware here at home, and I have it set up running VLLM. It is running and is able to give us back an answer. So I can push to it. Notice this. First of all, I'm defining the model, which is this. I'm using the Llama 3.1 instruct model. How many tokens I want it to get up to a maximum of 2,000. And I'm telling it I don't need it to stream, which is like the one word at a time. Just give me back the bulk answer. Collect it together. I'm setting the temperature to 0. Now, a little bit about that. In the model, as it generates, there's a level, there are these curves of probabilities that it will pick different words. And the temperature is the latitude at which the model can be creative, right? It's the best way to sort of phrase it. It will pick between some probabilities, flatten it to some degree if that's higher temperature, so that you can get different words, right, that it would predict as the next word. Instead of at 0, you just find the one that's absolutely the highest probable word. And by setting the temperature to 0, what I'm asking it to do, don't get creative. I just want the answers. Just give me the data. So we're asking it to be very concise. I know some people will say you should keep that slightly above 0, otherwise you can get into some repeat loops from the LLM. But in my experience, at least working with the Llama 3.1 8B and also the Mistral models, the temperature 0 actually does an extremely good job in giving good answers back. So what we're going to do is we're going to fire this off and have it answer back to us based on this content that's going to be sent in. So we're saying, as the role user, here's the content, and we're sending in this blob. We want the large language model to respond back. In this particular case, we're going to have Llama 3.1 respond back to us. So let's run that. Now what's happening is that the model's starting to go through and do its generation, right? It's going to crank through and create all those different tokens, and then it's going to give them back to us. And there they are. So here are some facts about solar in California based on the provided context. Sure enough, right? These are the things I wanted to see, things that are related to solar in California. And those are all coming from the blog post in a very summarized way with almost bulleted points, right? Now let's do this. Let's I want to clear the output here. Let's change this up a little bit. Give me some facts about cookies. How about that? Now remember, the context here I pulled was pulled for what? Is actually about solar in California. So it'll get interesting. We're going to hand it something that it's not going to make a lot of sense, right? So let's see how the model responds to that. Let's come back down here, and again, it's going to use that same context. We're going to push it into the model, and they get an answer. See what the answer is. What? Look at that! I don't know. That's right. I didn't give it anything. The provided context is about California solar and net metering. How about that? It does not seem to contain any information about cookies. Smart language model. Thank you very much. But part of this is also because we ask it to do that. Just say that you don't know, right? And so it did honor that. It followed those instructions. And again, back to the point that I made earlier, is this is a way to ground our answers so that we don't have it hallucinating. It could have created some. Like if I would have left that out, could have created, right? Just made up what it knew. It knows a lot about cookies. This language model, if we were to go and ask it, probably could tell us a lot. In fact, let's go and do that right now. So if I go over to, I have this model running through a really small chatbot. I'm going to switch over to right now. And we're going to paste that same question in there. Give me some facts about cookies. How about that? So if we hadn't given that we haven't given it the grounding through the content that we wanted it to use to answer, it would have come up with what it already had baked in to its weights. It's 8 billion parameters. It knew this, right? And some interesting things that it knew about cookie was that, look at there. Did you know where the word cookie came from? Wow, that's actually kind of cool. But that's not what I'd be wanting, right? So if I'm asking for something based on a corpus of documents I'm giving to it, I want it to only answer based on those confines. And that's one of the powers of this retrieval augmented generation. All right, so with that, we have covered what is RAG, right? Hopefully this give you enough to start to explore on your own. I'll create some links or add some links at the bottom of this video where you can download this Jupyter notebook, be able to run this stuff on your own hardware. If you wanted to actually run your own LLM, like the Llama, we actually have and run a chatbot. I'll send a link to that as well. You can download through TinyLLM. I have a small project page out there that talks about installing and running a LLM on your own hardware. Really useful if you wanted to try to pull together some confidential documents that you don't want to be exposed to maybe one of these big SaaS providers, right? An OpenAI or an Azure or Google or anybody else. Maybe you can't for whatever reason. This would be a way of being able to ground an LLM to give a conversational opportunity to talk to your documents and have it summarize, distill in some cases, just needle in the haystack, find something in all those documents in a really powerful way and provide a summary. So you can check this out, TinyLLM. I'll put the link in the notes below so you can download that and install something like that on your own gear. Well, with that, I appreciate your time and thanks. Please let me know if there's any additional things you would love to get covered. I think in a future session we would love to dive deeper into how transformer technology works itself, and we'll be doing that. But if there are other topics that could be interesting to you, please let me know, as I'm trying to put together just really a series of things that I'm learning personally, and being able to teach it is probably one of the most powerful ways of actually learning it yourself. So I'm sure I'm wrong on a lot of things too. I'm happy to hear any sort of candid feedback on areas that I should fix even in this presentation, or any of the documents are out there. So look for the links for the notebook if you want to follow along and run some of this code yourself, or you want to go and stand up a full-on RAG environment for your use, along with even a chatbot that you could take advantage of, like the one I showed. All right, well, with that, have a great day. Thank you.